Yeah, thank you very much. Thank you to the organizers for putting on a really lovely conference and for giving me the opportunity to talk to you today. I'll caveat that this isn't a laser cooling talk. This is more of an EDM talk. But obviously we use laser cooling, so it could be very interesting. Yeah, my name's Freddie Collings, so thank you for the introduction. It's a fairly brief talk, but luckily Tim Langen has told us that this is a good thing to do, to look for the electric dipole moment of the electron. And as a brief motivation, we know that there's not enough CP violation in the standard model to explain why there's more matter versus antimatter in the universe. And luckily, electric dipole moments violate CP symmetry. And so lots of the beyond standard model physics have electric dipole moments built in. And so by testing for an electric dipole moment, we can directly probe for beyond standard model physics. And the figure that we see on the right here just shows 10 to the minus 35 e centimeters is the prediction for the standard model value of the electron's electric dipole moment. And the current experimental upper limit is set by the Cornell group in Gila, where they've set 4 times 10 to the minus 30 e centimeters. So that's the benchmark that we want to try and sort of push against. And Imperial, we think using ytterbium fluoride is a very good way to do this measurement. And that we can tell by looking at the statistical sensitivity as a measurement like this. So some terms that you see in the denominator, we can see that the effective electric field of the molecule, which is sort of the enhancement that the electron sees compared to a laboratory frame, is very important. The amount of time that you can use in your measurement, the coherence time, helps to improve the sensitivity, and also the number of molecules that you can get in your measurement. And so ytterbium fluoride, it combines a relatively large effective electric field. So we see up to 25 gigavolts per centimeter when you fully polarize the molecule. And also it's laser coolable. So that gives us some advantages, that it's got an optical cycling transition, so very good for detection. And we can cool them so we can get a large number of molecules involved, as well as given our EDM sensitive state as the ground state, we have a potentially unlimited lifetime. So if I take you through our experiment, we start with a buffer gas source of ytterbium fluoride. And we have a 4 Kelvin source at the moment that allows for 150 meters per second moving beam of ytterbium fluoride down the beam line. We then put this into a 2D transverse laser cooling region, where we can nicely collimate our beam down to sort of a centimeter sized beam. And this experiment is very long as a beamline. It's about 5 meters long, and we don't see much appreciable expansion of the beam over the full length. We then optically pump our molecules into the rotational ground state and the rotational hyperfine state. Sorry, the ground hyperfine state. And then they enter this interaction region. And this is the sort of heart of the experiment, where we have very well-controlled magnetic fields and very well-controlled electric fields. And we use a state preparation stirrup. The molecules can pass through these beams and adiabatically transfer themselves into the first hyperfine state. And we control the polarization so that we create a superposition of the stretch states, so that the spin is aligned along the z-axis. And the z-axis here is the same as the magnetic field we apply and the electric field that we apply. And this allows the spin to precess around, depending on the strength of the magnetic field. And if there is an electric dipole moment, the strength of the electric field. And when we read out this phase at the end of the experiment, this turns into a population difference, which we can then measure independently using an optical cycling transition from the first rotational state and some microwaves to transfer them from the ground state to the first rotational state. And we've worked recently on looking at this fluorescence detection, both in some PMTs for some temporal resolution, as well as some cameras for some spatial resolution. And recently we've been working on trying to get the cameras fast enough so we can get some velocity selective detection as well. It's an Ultracold Molecules conference, so I have to tell you about our laser cooling. We have a 20 centimeter region, and we use a magnetically assisted scissors effect to do the laser cooling. And if we look at the end view of the molecules, if you see the molecules coming upstream here, without any laser cooling, our cross probes fully highlight completely filled with molecules, but when we add the laser cooling, we can nicely collimate this step down. And if we look at the side view with the PMT, we can see as a time of flight, we see a huge increase in the number of molecules when we use the laser cooling. So to give you some numbers, we see well over 1 million molecules per shot. We have a 7-fold increase compared to when we don't do any laser cooling. And this gets better for the slower moving molecules, so it gets up to a peak enhancement of 9. Then to the heart of the experiment, one flaw to using ytterbium fluoride is that we use this ground state, which is magnetically sensitive. And so because the G factor is 1, we have to very well control our magnetic fields to not add additional noise to the measurement. And so some requirements we have, any correlated fields with the direction of the electric field could be a systematic that we can't distinguish from a real electric dipole moment. And so we have to be able to measure these E-correlated B fields down to sort of 100 attotesla in sort of a reasonable time frame that it doesn't slow our measurement down. And the noise also has to be kept at a low enough level to not add noise to the measurement. And so we've set this bound at 114 femtotesla per root hertz. And if you can see in our diagram here, we've created this lovely low noise measurement environment with 4 layers of mu metal shielding and a choice of materials that are not very electrically conductive to reduce the thermal magnetic noise that they can contribute. We also have a nice array of Q-spin surf magnetometers. So we have really good magnetometry inside this region so that we can measure these E-correlated fields as well as check on the noise. So some results of this, if you look at a noise spectral density of the magnetic field, you can see at 1 hertz, which is maybe a frequency that we can use to switch the electric field direction. That's the frequency in which the noise may contribute from the magnetic field. We get down to 40 femtotesla per root hertz. And so that's equivalent to an additional noise of 2 × 10⁻30 E centimeters in a day of data collection, which is well below our shot noise sensitivity at the moment. And we also can take E-correlated measurements as well, and we get to a precision of about 110 attotesla in a very reasonable time frame of only 104 hours. And we released something on the archive recently, so if you have any further questions, you can have a look at the paper and talk to me. For our state preparation, we've worked quite a lot on this as well. So we need sort of high efficiency, we need it to be robust against imperfections. And so we do a stirrup scheme where we allow the molecules to sort of move themselves through these beams and adiabatically transfer themselves into the correct state. This is sort of very sensitive to the 2-photon frequency difference. And so given in our ground state, there's only 170 megahertz of difference here. We can use 1 laser and just use an AOM to shift that frequency. And that has a good benefit of meaning there's very little phase noise between the 2 arms because we're only using 1 source for the laser. And the asymmetry here is the measure we use is a normalized difference between the 2 quadratures of the interferometer. And we can see when we have the correct 2-photon detuning, we get a nice transfer of about 85% at best. And then if we use the stirrup at the end of the region as well, we can create some fringes. So if we use a different magnetic field for each shot, we can trace out these nice spin precession fringes. And when we use the full time of flight with all different velocities, you see some sort of dephasing here just due to different velocities acquiring different amounts of phase in the measurement, but we can also select a particular velocity class, and this allows us to get some nice contrast fringes up to 0.75. So we can plug all those numbers into the statistical sensitivity we had at the start, and at the moment, we're looking at a statistical sensitivity of 9 × 10⁻30 e centimeters per day. So a caveat, we're not at that noise level yet. We need to still identify sources of noise in our experiment. But if we can push that down, then 100 days of data collection would mean we'd be competing with the best measurement to date. I'll quickly run you through a future upgrade that we're thinking about. I told you we had a 4 Kelvin buffer gas source at the moment. We've also characterized a 1.8 buffer gas source, Kelvin buffer gas source, where the molecules coming out can be a lot slower. So in the plot on the right here, you're seeing if you take the temperature down, you can increase both the number of molecules you have coming out, the flux, as well as drastically reduce the velocity of the longitudinal velocity of the molecules coming out. So we're working on building up this source, and that would even bring our statistical sensitivity down further to 5 × 10⁻30. So I think I'm out of time, so I'd just like to thank you and show you the team that we have. And yeah, any questions?
Questions? So I have a question for you. What is your current precession time, and what are the prospects for creating a YbF MOT and eventually doing these measurements with the molecules trapped?
Yeah, that's a good question. So yeah, if we look at this equation here, we are using a 5 millisecond precession time at the moment. If we can get a slower source from this new source, we can get to maybe a 15 millisecond coherence time. Then if we manage to create a YbF MOT, then the thought is we can get a much larger coherence time. And the way it scales is the coherence time there's no square root there. So the number of molecules matters slightly less than the coherence time you can get. So with a YbF MOT of maybe a second of coherence time, this would drastically improve the sensitivity.
Thanks. More questions? All right, if there are no more questions, let's thank Freddie again.
Thanks very much.